All right, this is our final lecture with material to cover. So the plan today is very short lecture to finish the autonomic nervous system. Probably like a half an hour. Maybe because I talk too much, maybe 35 minutes. So I want to finish the autonomic nervous system, and then the rest of the lecture is all yours. I have brought with me copies of exams 1, 2, 3, and 4. Now that everyone has taken exam 4, I can give you back the Scantrons. Okay. Don't forget, those of you that have lab tonight, our last meeting, nervous system practical, cow eye dissection. That's it. Next week, next Tuesday, final exam. No meeting in lab next week. If by chance there's a snowstorm, we have Thursday, right? Really? Dry or wet? I'm making a face, can't see it. Nancy has a public service.
Oh, okay. So Sarah's wonderful idea, part of the students in this class, to invite everybody next Tuesday to join us for a drink at Juniors. So after we have our finals, and the professor will come and go. Just like stress, have a drink.
She called it too, didn't she say you're like already running to get a drink after?
You're going to be planning your.
Yep.
You know, not every class has as nice of students as you all do, so it's really nice.
That's why you're invited.
Well, some classes are just really quiet. They don't really talk to each other, but it's nice. I mean, you're all working, doing this, doing that. You're kind of in this together. So I think it's really nice.
No pressure.
No, the 60 was there. If you go a little bit further down that way. Right, there's a new, right before the circle, there's a shopping center on the right. So there's doors and there's. But it's like. Yes, it's like a bar restaurant.
So let's all go on the final, and let's get wildly inebriated.
Oh, the young one. To be young again. That's very nice. All right, so let's go ahead and finish this, and then you'll have the time that you want to do whatever you like. So we began this discussion on Tuesday. Let me remind you what we're talking about. We are talking about the peripheral nerves, the peripheral motor nerve, right? So we're only talking about motor nerves sending impulses away from the brain spinal cord. And this system is made up of the motor nerves that supply what kind of muscle? Cardiac and smooth. So the autonomic nervous system, autonomic kind of sounds like automatic. Aren't cardiac and smooth muscle involuntarily controlled? Cardiac and smooth muscle is automatic, autonomic. By the way, what does somatic mean? The somatic motor nerves. The somatic nerves supply what kind of muscle? Skeletal, right? So the somatic motor nerves go to skeletal muscle. We discussed that last chapter. This chapter is all about the motor nerves that go to smooth and cardiac muscle. This autonomic nervous system, because it supplies our smooth and cardiac muscle, helps to regulate all of our major organs. Does that sound familiar? So we can deliver certain motor nerve impulses at certain times to increase or decrease heart rate, to increase or decrease GI tract activity. All the above. To constrict to constrict arteries more or less, to help regulate blood pressure. You name it. These motor nerves, because they supply cardiac and smooth muscle and send nerve impulses at certain times to control all of our main organs. Sound good? And it does it through what we call that visceral feedback loop or visceral reflex. But it's just what we already know. Remember, the spinal cord and brain is constantly receiving sensory input from these major organs. I gave you the example of the stomach, didn't I? There's stretch receptors in the stomach. If they sense too little stretch, those sensory receptors will send a message to the spinal cord and brain. Hey, we're hungry. The brain's gonna alert the hypothalamus to make you feel hungry and eat. And then eventually it's gonna send motor impulses out to your stomach wall, take up the smooth muscle, to contract, to help process the food. Good. I keep repeating it because it's a little bit more conceptual. If it's not getting through, you let me know. This is my last ANS lecture. I'm all hot and bothered up here. Take my vest off. Okay, so now that we understand the basic function, we want to talk a little bit about the structure. Come on, it's the last lecture. I had to do a compare and contrast. It wouldn't be the same without it. We've already talked about somatic. I just reviewed it, didn't I? Yes? Somatic motor nerves supply what kind of muscle? Skeletal. Now we're going to add on to that. We already know this. When we talked about, I know I keep bringing it back, the neuromuscular junction. Is this like a... When a motor neuron goes to a skeletal muscle, what neurotransmitter is released across the synapse to a skeletal muscle? Acetylcholine. And it's what we call a one neuron chain. Let me draw a picture. Well, it's a little bit more complicated than that. All right, here we go. Brain. That is not a bad brain for me. I just want you to know it's not a bad brain for me, right? And the spinal cord. So let's say that we're talking about a somatic motor nerve, which is going to a skeletal muscle, right? So I have a skeletal muscle out here. This motor neuron, we're talking about a motor neuron, is what we already think of. It's a one neuron chain. In other words, the cell body is in the spinal cord. And then we have that one long axon that goes to the muscle. So the cell body, remember the gray matter of the spinal cord? Isn't the gray matter of the spinal cord cell bodies? So imagine, we have the cell body. Remember the cell body and then the axon? What I'm pointing to here is the cell body. It's in the spinal cord. And then it's just one axon to go to the skeletal muscle. So it's what we call a one neuron chain. It's going to be different for the autonomic nervous system. So we've already reviewed the autonomic nervous system, motor nerves that supply, cardiac and smooth muscle, So not only can we use acetylcholine as a possible neurotransmitter, but when we're talking about these autonomic nerves, we can also utilize norepinephrine. So that's a difference. When we're talking about the motor nerves that supply skeletal muscle, the neurotransmitter is always acetylcholine. When we're talking about motor neurons that are autonomic, that go to cardiac and smooth muscle, it's sometimes acetylcholine, but it's sometimes norepinephrine. But at Seinfeld, where George got a cheap suit, but it was like corduroy, and it kept going. We'd be at the office, you know, like, then if someone else stopped, you stop. What's that noise? I don't know. They walk. Another difference is in the autonomic motor nerves, instead of just having one neuron, we have two. Let's compare and contrast. Let's say now we're talking about the stomach. That's a really bad stomach. But the stomach is covered by smooth muscle, right? So now let's look at a motor neuron that's autonomic, that's going to the stomach. We're going to have the same thing, a cell body here, and one neuron. But then we're going to see a synapse. Then there's going to be a second cell body. And that second cell body is what goes into the stomach. So anytime we have a motor nerve going to smooth or cardiac muscle, it involves two neurons. Does that make sense?
Always just two, not more.
Always just two. The two motor neuron chain. So I could have drawn the heart. I could have drawn any motor nerve impulse going to smoother cardiac muscle. It's got two neurons.
Is it only in the sensory division of the peripheral nervous system or can happen to first degree, second degree?
I believe so. It is my understanding that here only two. So why do you think this is? What possible benefit could it be to have two neurons? Wouldn't it be less efficient? Because now we got to go through the process of sending an action potential, depolarizing, repolarizing. We get to the end of that first neuron. We got to release a neurotransmitter to cross into the second cell body. What could be the possible benefit? Big fur. Do you ever go to Boscov's? You think it's just for old people, but Boscov's? It's more like this. If you're in the mood to shop, you want to look around, you can find some stuff. Black turtlenecks. It's family run. Don't you want to support a family run business? There's a Boscov's, what, at Clifton Park Center? Colony Center? Yeah. I'm just telling you. What's that? Yes. It was a department store, but it's mostly clothing, but they have linens, like sheets and like a cheaper Macy's, like a JC Penney's, but yeah. I'm just saying. You wouldn't think this would be an old person. Or maybe you would.
I have one of those. You're not allowed.
I'm just saying, if you're in the mood to like look, There's like an old age. There's an old person section, which when I'm older, I'll go there. You know, like this sweaters with the quilted flowers, bird on it. I just loved it. I found my brother like a Levi leather jacket, like $100 there. I was a hater at first. I'm like, I don't want to go to Costco. But you got to be in the mood to like look, you know. So what's the benefit? What's the benefit of having a 2-neuron chain? The benefit is that we have the opportunity to alter the neurotransmitter release. So not only can we release a neurotransmitter here, we also release a neurotransmitter here. So it gives us a wider range of options. I'm not going to ask you this on the final, but for those who are interested. Yeah. Because right. So now we have the ability to release acetylcholine here and then norepinephrine here.
I mean, do you want to have the option for it?
Sure. Sure.
Okay, can be both, right?
Norepinephrine can be both. Acetylcholine is going to be excited for it. But just the fact that we have another synapse, it just gives us more range of options and allows us to better control. This is more complicated than a skeletal muscle. I mean, a skeletal muscle, either we want to contract it or not, is kind of simple. We're not going to get into the details of which neurotransmitter is released here versus there and why. But so it's a 2-neuron chain. Of course, we call the first one the preganglionic neuron, and we call the second one the postganglionic neuron. Why? Well, what is a ganglion? So the dorsal root ganglion was that bulge on the dorsal root. The reason we called it a ganglion, anytime we see a ganglion, it is a cell body outside of the CNS. So the dorsal root ganglion, isn't that a cell body outside of the CNS? It's close to the spinal cord, but it's not in the spinal cord. So anytime we see a neuron cell body outside of the CNS, it's called a ganglion. Ganglia for plural.
Is it be a cluster of somebody's or can it just be one?
It's always going to be a cluster. I mean, yeah, it's always going to be a cluster. So here we have a cell body outside of the CNS. So this cell body right here, right? So the neuron before it is called the preganglionic neuron, before the ganglia, which is a cell body outside the CNS. And this one is called the postganglionic neuron. Good. All right. Before we talk more about the specific anatomy, let's talk about the 2 functional divisions. Everyone's probably heard of sympathetic and parasympathetic, right? Your fight or flight. Let's just write it out of it. Let's try and simplify it. So it tends to be that these autonomic motor nerves kind of contract or relax in this way or that way. There's only really 2 responses. These autonomic motor nerves will contract in a way to create a sympathetic response, or they'll be stimulated in a way to make a parasympathetic response. It's really it. So the first thing is that, let me use black, make it easier to see. The sympathetic. So now we're talking about function. Your autonomic motor nerves are in this response anytime you're under stress. So the autonomic motor nerves send nerve impulses in such a way that's considered sympathetic anytime we're under stress. It could be a gun to your head, could be a bear chasing you in the woods, but it could also be other stresses like exercise. Isn't exercise a stressor to the body? Yes, it's a good stress usually. So it's not always life-threatening. Maybe you're stressed about an exam coming up. Maybe you have like some emotional stress, something's going on. Anytime your body is trying to handle stress, the autonomic motor nerves will fire in such a way that is considered sympathetic. When we're in this sympathetic, which by the way is called fight or flight, right? Because when we face stress, if we think about it in caveman times, what's the best way to handle a serious stress? Fight or get the hell out of there, flight. So your autonomic motor nerves will cause an increase in heart rate, respiratory rate, and blood pressure. It will increase blood flow to skeletal muscles of your limbs. So it's almost like it's pre-wired. All of these connections are pre-wired. And when your body encounters stress, your brain just flips a switch. And all of these autonomic motor nerves activate. Body's under stress, we're gonna increase the heart rate, increase the respiratory rate, increase blood pressure, we're gonna send more blood flow to the muscles. Because what do those things help you do? Handle the stress. If I'm exercising, I'm purposely adding some stress, I want my heart rate to go up. If I'm running from a bear, I want my heart rate to go up so I can pump out more blood to my muscles and get out of the way. Now, what do you do when you see this?
Make yourself really big. Depending on the bear. I just read. It depends on the bear. One, you make yourself bigger and try to take it away, destroy. The other one, you take it.
How could you relax?
You gotta play it or eat it.
Honestly, this discussion seems much more relevant to helping me survive than this crowd. Cares about the autonomic motor nerve, how they work. Now, we only have a limited amount of resources. We only have a limited amount of blood. We only have a limited amount of ATP. So when your autonomic nerves cause this, it means that we have to take from somewhere else, right? So while this is happening, we decrease our activity, our nerve impulses in blood to the gut, your GI tract, and the kidneys. Because in that moment of stress, it's really less important if you digest your breakfast. The GI tract activity, so nerve impulses and blood flow. Because in AMP2, we'll talk about this, we're able to kind of shunt blood to where it's most needed. I mean, you only have 4 to 6 liters of blood. Let's face it, we have a heart and a bunch of pipes. but we can determine where to best send the most blood flow. So when you're facing stress, more of that blood flow, more nerve impulses go to what's going to help you handle the stress. And in that moment, we just reduce some of the blood and nerve impulses going to our GI tract and kidneys. You don't stop it altogether, right? It's not like, oh, we don't care about our GI tract, let's just not give it any blood. We just reduce the amount. So then the other way the autonomic nervous system will function is the parasympathetic, right? Parasympathetic is what we call our resting and digesting. You can see the green okay, right? You would tell me if you could. So in other words, if we're not handling stress, then your autonomic motor nerves shift into this mode, a parasympathetic mode, when you're resting and when you're digesting, if you just ate. So we basically flip this around. Now we're going to increase our blood flow and our nerve impulses to our GI tract and kidneys. And now we lower heart rate, respiratory rate, and blood pressure. We don't send as much blood flow to our skeletal muscles. Right now, you're relatively in a resting position. Your skeletal muscles don't need as much blood. They're not really doing much. So now is when your body can afford to put more blood flow and more nerve impulses here. Our autonomic motor nerves are already kind of wired this way. They're either kind of in a sympathetic mode or a parasympathetic mode. All these things are here. What I want to point out is something called dual innervation. That just means that all of our organs are innervated by both sympathetic and parasympathetic. I'll show you again, hold on.
All organs are just some.
All organs. Aside from skeletal muscle, because that's somatic, but any autonomic supplied organ. So I'll go with my stomach again, right? I cannot draw a stomach. Let's say the red is sympathetic and the green is parasympathetic. So we may have a parasympathetic cell body coming out here to another cell body coming out to the stomach. So each organ has a nerve supply that is going to act as a sympathetic responder, and it's also going to have one that is parasympathetic. By the way, we talked about the vagus nerve. Is that a sympathetic or parasympathetic fiber? Parasympathetic. So this green one could actually be a branch of the vagus nerve. That was an example of a motor neuron that is parasympathetic. But we also have motor neurons that are sympathetic. So if a nerve impulse fires down the green one, what is its action going to be at the kidney? I mean, at the stomach. Correct. So if if I send a nerve impulse down the parasympathetic fiber, it will increase activity of the stomach. What if I send a nerve impulse down the sympathetic to the stomach? It'll reduce stomach activity. Now, if we were talking about the heart, it'd be a different case, wouldn't it? So let's say we have the heart. Let's do a sympathetic fiber. If I send a nerve impulse down the sympathetic fiber to the heart, what will it do to the heart? Increase heart rate. Because what is the sympathetic response to the heart? Goes up. Versus, what if I send a parasympathetic? If I send a vagus nerve impulse to the heart, its effect is parasympathetic, it will decrease heart rate. But dual innervation means that every organ is innervated by both sympathetic and parasympathetic. Dual innervation just means that every organ is going to receive a sympathetic motor neurons and parasympathetic. This is saying the same thing we already said. I give you more information, you only need to know what we wrote down, right? Good. Okay, now we're going to talk about the anatomy, and this is going to go much faster. There's an N chart. This is helpful. I also really like this picture. So we're going to look at the anatomy of three things: where the sympathetic and parasympathetic nerves originate from, the length of the pre and post ganglionic neuron, and then where the ganglia is located. This is just memorization. Let's look at the sites of origin. This is a lot of words to say something quite simple. The parasympathetic motor neurons originate in the cervical region of the spinal cord and in the sacral region of the spinal cord. The sympathetic motor neurons originate in the cranial region or cervical region and the sacral, the top and the bottom. See the purple? These purple are parasympathetic. They come out of the spinal cord high and low, which means that the sympathetic leave the spinal cord in the middle. The sympathetic leave the spinal cord in the middle. The green. Parasympathetic leaves the spinal cord high and low. Sympathetic leaves the spinal cord in the middle. Let's talk about the length of the fibers. Parasympathetic has a long preganglionic neuron. So that, because remember, these are two neuron chains. In the parasympathetic motor neurons, that first neuron is long. Look at how tiny the second one is. So the first neuron in the two neuron chain is long, and the second neuron is short. Long, short. The sympathetic is the opposite. The sympathetic has relatively shorter preganglionic and longer postganglionic. You could even memorize one and then the other is just the opposite. Never done that. Good. And then the last one goes along right with this, the location of the ganglia. The ganglia are the cell bodies outside of the spinal cord. In the parasympathetic, the ganglia are in or near the effector. Which makes sense because we had a long first neuron and a short second one. So the cell body of the second one, or the ganglia, is in or near the organ. Versus the sympathetic, because the first neuron is shorter, the ganglia of the sympathetic are close to the spinal cord. I actually quite like this diagram because it compares everything. So it shows us the somatic. Remember? The somatic is going to, the somatic motor neurons supply skeletal muscle. The somatic motor neurons release acetylcholine. And the somatic motor neurons, it's a one neuron chain. The autonomic motor neurons supply cardiac and smooth muscle. The autonomic motor nerves have a two neuron chain. 1, 2. The autonomic nerves can release either acetylcholine or norepinephrine. And then when you compare sympathetic to parasympathetic, sympathetic has a shorter first nerve, shorter preganglionic nerve, longer postganglionic nerve. The ganglia is therefore closer to the spinal cord, versus the parasympathetic has a longer preganglionic nerve and a shorter postganglionic nerve.
The parasympathetic can't do the acetylcholine, or sorry, can't do norepinephrine.
So there are some specifics, but you don't have to know those. Yeah. So there are some specifics, but you don't need to know which neurotransmitter is released where. Couple odds and ends, and then we'll be done. All right. I already mentioned dual innervation, right? All of our organs in our thorax and our abdomen are supplied by both sympathetic motor neurons and parasympathetic. Now I'd just like you to understand when we talk about a tone, not the tone that your kids give you. My mom, I don't know about you guys, but my mom, like, I could probably curse, come late after curfew, but like if I gave her attitude, that was worse than anything else in the world. What this just means is we're always having some activity in both. There's always going to be a sympathetic tone and a parasympathetic tone. It just means that it's never all or nothing. In other words, it's never that the stomach receives only parasympathetic nerve impulses and zero sympathetic. That's not how it works. Your stomach is always going to be receiving some of both. So we have a continual quote unquote tone. Just meaning that no matter what's happening, there's some activity in both sympathetic and parasympathetic. So it just means that when we overall want a sympathetic response, we just send way more sympathetic fibers than parasympathetic. We may send like 90% sympathetic nerve impulses and 10% para. But there's always going to be some low-level activity of nerve impulses in both. We consider that low-level activity, no matter what, a tone.
Why, what those tones do?
No. We don't have to know that. I mean, the reason why we have that is it just helps us better prepare. So if we always have a little bit of activity of sympathetic when we want to go from breastfeeding to a bear's chasing me, I already have some sympathetic already started. I'm not starting from completely zero. All right, a couple random things that will be done. When we talk about what's overseeing the autonomic nervous system, in other words, what is flipping that switch? No. What's flipping a switch to alternate between sympathetic and parasympathetic? Well, it involves many parts of the brain. All I want to point out is the hypothalamus plays the biggest role. So when you're talking about what is controlling whether we are doing sympathetic or parasympathetic, it involves multiple parts of the brain, but the hypothalamus has the most function in overseeing it. Correct. It's controlled mostly by the hypothalamus. I like how it calls it the boss. Like the mob boss. All right. Two more things really quickly. I just added these two slides the other day. I did put on Blackboard this updated one. This is not going to be on the final. Have you ever heard of heart rate variability? What's that? I haven't heard much about it, but if you notice, I have this like called a whoop. So as an athlete, I'm trying to measure recovery and whatever, and even like the Apple Watches, you know how they measure your heart rate? Well, one of the really helpful metrics for the autonomic nervous system is something called heart rate variability. This is not on the final, but if you're interested, what it is it's a measure of the variation in beats during a minute of your heart. So for example, if your heart rate is 60 beats per minute, it's not that every millisecond it beats once. You know what I mean? If those heartbeats over a minute were evenly spread out, if my heart rate was 60 beats per minute, and there are 60 seconds in a minute, my heart would beat every second, right? But it's not that evenly spaced out. One may happen, it should be seconds, right? One may happen at 1 second, and then it might happen a little bit sooner, 1.8 seconds, and then 2.5. As it turns out, the higher this variability, it shows that your autonomic nervous system is better prepared. Which at first I thought was kind of backwards, but it just means that your autonomic nervous system is prepared and ready. It's that constant tone. We actually want to be a little push and pull between the parasympathetic and sympathetic. My Whoop has been measuring it. I know this is like so ridiculous, but this is over the course of a semester. As I've been working more, look at my heart rate variability. But then over Thanksgiving break, I got a little bit of a recovery. So it's really useful as a measure of recovery. Okay. All right, the last thing is I want to talk about referred pain. Last thing. For those who want to look at exams longer, if you were in Tuesday's lab and you want to stay after to look at exams more, you can. Thursday's lab section, it won't take the whole time tonight. So if you want more time after our how I section, we can look at exams more. Okay. What is referred pain? Where you feel pain somewhere else, right? So a good example is the heart, right? Someone's having a heart attack. They may feel pain in their jaw, or they may feel pain in their left arm. The referred pain is when you have pain somewhere else. If it's my heart that's the problem, why on earth do I have pain up here? Another interesting one is called Kerr's sign. Someone with liver problems might have pain on the right shoulder. This has to do with our sensory. So up until this point, we've been talking really only about motor nerves, right? We've been talking only about motor nerves. Now we're going to step back for a quick second and talk about sensory. Brain. Let's do the heart, right? So the heart is here. Then I have my left arm. Here's the spinal cord. So what's happening in referred pain is that we have sensory nerve impulses. If there's pain in the heart, I'm going to be sending sensory nerve impulses of pain back towards the spinal cord and brain, right? Well, it just so happens that there's also going to be some sensory nerve fibers from the left arm. And we know that our nerves are bundles, aren't they? So what happens is this joins the same bundle as this. So the sensory nerves from your heart sometimes end up joining the same nerve bundle from your arm. So when it gets to your brain sometimes can't differentiate whether that sensory nerve impulse came from the heart or the arm. Even though the sensory neurons were separate here, they eventually join the same bundle. So you have one axon from the heart, one axon from the arm that are side by side. So when that bundle goes up to the brain, your brain might confused, and it might mix the signals a little bit. So the sensory nerves might end up joining the same bundle before it goes back to the heart. Anything else we didn't cover is not on the final. All right, I'm going to pass back your exams. And I'm going to make some old exams available. An hour, but we can extend it. And then for those that have the practical, after we're done, you can look at the exams again. You know me. Exams 1, 2, 3, 4. One of each. Please only take one at a time.
How many points do I have? Under 25 questions. I don't make points.
It'll be a percentage out of 100.
That's a quarter of our grade.
It's a quarter of your grade. You'll divide whatever number you get 125 and divide by 125. So if you get like 120, you get like 120 out of 125. What's that? 120 divided by 125 is 96%.
Each question.
Oh. All right. More of them get more wrong.